Hello everyone, I'm Manav Agarwal from the Indian Institute of Technology, Roorkee, and today I'll be discussing the topic of visualizing spectral decomposition. We're gonna cover a lot of aspects such as the matrix transformations, the matrix decomposition, the algorithm, and its time complexity, as well as the applications that spectral decomposition offers to us. This is a part of the DA 201 Applied Linear Algebra course mentored by Professor Mayank Goswami, and I'm a second year undergrad student of data science and artificial intelligence. So let's explore this topic without delay. First of all, what is a matrix? What comes to your mind when you think of a matrix? We've been too used to the traditional mathematical formation of a matrix. Let's talk about its role in applied linear algebra. So the very essence of a matrix is its role in producing transformations to vectors in the vector space. This is how a matrix looks. Now, when we talk about transformations, three particular types of matrices become very important as they tend to form the very basis of all possible transformations. This involves the diagonal matrix, the orthogonal matrix, and the shear matrix. Taking further upon the diagonal matrix, this has the ability to scale the axis of the vector space when used as a transformation. Now, this is really interesting how a matrix has the effect on a vector space. Whenever applied, it can transform the entire vector space. For the diagonal matrix, this is in the form of scaling the axis. The ith diagonal element is capable of scaling the ith axis. For example, if we consider the following matrix, the element A11 would be able to scale the x-axis. Correspondingly, the A22 element would be able to scale the y-axis. So on. This can be multiplied to any number of dimensions. The concept remains the same. A diagonal matrix can thus be used to perform two very critical roles. Number one is scaling, and the number two is reflection. Scaling can be performed by considering a positive scaling factor along the diagonal, whereas a negative scaling factor would cause reflection. A better visualization would be considered in the upcoming slides. So let's take it forward. Secondly, we discuss the orthogonal matrix. This has the ability to change the basis of the vector space when used as the transformation. It is essentially a rotation transformation. It follows the following property. First of all, the orthogonal matrix is special as its transpose serves as its inverse as well. Now, how to identify such a matrix? A very important property is that the modulus of any row or column vector would always be equal to 1. Secondly, a set of row vectors or a set of column vectors, when taken together, are orthogonal to each other. That is, dot product of any two row vectors or any two column vectors would end up giving us 0. Now, an important thing to note is that if multiplication by an orthogonal matrix is a rotation operation, then multiplying by its inverse or transpose is a rotation operation in the opposite direction to achieve the original axis. Now, why I said transpose is particularly associated to the concept of spectral decomposition. Let's get to that in a while later. Talking about orthogonal matrices, applying Q would essentially rotate the plane and take it to a new set of axes. Now applying Q transpose, we see that we can perform the derotation operation. That is, the transformed vector axes come back to the original set of axes. Let's take upon the next type of matrix, that is the shear matrix. As the name suggests, this matrix has the ability to shear a plane in the vector space by incorporating a scaling factor to more than one axis in some of its column vectors. Now, how to look at it is that if we consider the very same diagonal matrix with all elements of the diagonal, let them be 1. But in the fourth column vector, we can see that we have added another scaling factor lambda to the first row. Now, what this does is it will perform a sharing operation on the plane which it is applied on. We've been familiar to the process of sharing, I believe, in our JE days when we used to study how if we put pressure upon a plane from the side, it can actually bend and change its formation. That is, we can disform the figure. So let's take upon the matrix composition topic. Every transformation matrix is essentially a composition of the ones we've discussed so far. That is, as I mentioned, that those three matrix transformations form the basis to any possible transformation in the vector space. Thus, any matrix can essentially be represented as a composition of three particular types of matrices. For example, this matrix represents a net transformation, that is minus 2.5, 0, 0, and zero point 0.6 can actually be broken down into three different operations. That is the elementary forms of transformation. When we talk about the first transformation, we see that it is a diagonal matrix with a scaling factor in the x-axis. That is, we are magnifying the x-axis because it is positive and greater than 1. Talking about the second matrix, we are applying a scaling transformation to the y-axis. And here we are actually shrinking the y-axis because the scaling factor is actually less than 1 and it is yet positive. Talking about the last transformation, we are actually taking a reflection operation by applying a negative scaling factor along the x-axis. Thus, what this does is a reflection about the x-axis, that is negative scaling. Let's take an example. This is a very famous fountain building of IIT Roorkee. Let's talk about the transformations on the image grid of this particular slide. So, first of all, we are talking about scaling the x-axis. How will it look afterwards? Is like this because the x-axis has been magnified. Similarly, now taking up the second operation, that is scaling the y-axis. As you see, the y-axis has been shrunken due to this scaling factor, which is less than 1. Talking about the final transformation, we talk about the negative scaling along x-axis. That is minus 1 scaled, which causes reflection about the x-axis. Thus, we see what we have ultimately reached. Now, the amazing thing is these three transformations, when combined and represented as a single matrix, are actually the one which we had seen earlier. The original image is this. This matrix will be representing the net transformation. That is, on applying this on this image, we would actually get the very same result as we got from those three broken transformations. And very interesting aspect is that such transformations on image matrices are a key part of important ML and deep learning processes such as data augmentation. For example, if we ever fall short of like image data, we are able to multiply our data set by applying such rotation and reflection operations throughout our image data sets to multiply them many-fold. This has actually been used in several CNN applications and serves as an important tool in the ML and deep learning processes. Talking about matrix decomposition, finally, we are going to touch the base of spectral decomposition. Now that we know that a composition of transformation matrices helps to form a net transformation matrix, we should wonder upon how to break any such transformation into its sub-transformations. This is where matrix decomposition comes in. So now you can actually get a idea of what spectral decomposition actually means. It involves breaking down the net transformation into its components of sharing, scaling, and rotation. This is what matrix decomposition actually is. Now we get to the topic of what actually is spectral decomposition. Spectral decomposition actually deals with the decomposition of symmetric square matrices. Now, why have we given a special name to this particular matrix? That is because a special matrix is the symmetric matrix which induces complex transformations when applied. But in order to understand its component transformations, decomposition is not going to be easy. That's where spectral decomposition comes into play. A symmetric matrix serves the property that its transpose will ultimately lead us to getting the original matrix on which we have taken the transform operation. Let's talk about eigenvectors. Trust me, you wouldn't have experienced the concept of eigenvectors as deeply as you are going to today. Every matrix as a transformation essentially represents a distortion in the vector space, causing each vector to skew away from their original axis. But here's the catch. Will this be applicable to every vector in the vector space? or is there some exceptions? Here we can see that a particular set of vectors is never skewed off its axis despite the number of transformations which are part of the matrix composition. These are indeed the eigenvectors of the matrix. So now you can actually see the gravity of the concept we have been learning since our semester one. Let's visualize this. As you can see, the first matrix does not possess any eigenvector. So whenever transformation is applied on the vector space, the vectors will always skew off their original axis. In the second matrix, we have one eigenvector. Thus, when visualized, an eigenvector can only be scaled along its original axis. It won't actually skew off its original axis. And in the final matrix, we can see that we have achieved two eigenvectors and we see that they do not skew. Rather, one is simply scaled along the original axis while the other is negatively scaled along its original axis. This is the very concept that eigenvectors hold, and it's so important in our visualization aspect as we can see that the entire decomposition process shall revolve around this. Now, talking about eigenvectors further, we need to understand that why are symmetric matrices so special? The fact is that the eigenvectors of a symmetric matrix are orthogonal to each other. They are perpendicular to each other. Why is this important? This is because it becomes an important property as this enables the eigenvectors to perfectly coincide with the standard basis when transformation is applied. That is, we can expect the eigenvectors to always serve along the original or standard basis taken by the vector space whenever transformations are applied. This 90-degree angle between the eigenvectors will be helping us to coincide with the multi-dimensional basis we take. So on, we can align the eigenvectors of a 2 cross 2 matrix, for example, along the x-axis, the y-axis. For a 3 cross 3, if we are able to achieve three eigenvectors, we can align them along the z-axis as well, and so on. Let's talk about spectral decomposition as it is. We've finally acquired all prerequisites to understand, and let's see what spectral decomposition actually involves. The transformations represented by a symmetric matrix can thus be decomposed as S equal to Q lambda Q transpose. How this does is Q transposition would actually be serving as a rotation transformation from the original eigenbasis to the standard basis. The scaling lambda factor would actually be scaling the axis and provide us magnification or shrinking operations along a particular basis. The final Q matrix would actually derotate and bring back the plane from the standard basis back to its original eigenbasis. To better understand this, here is a proper visualization. Let's talk about a symmetric matrix with A and C as its diagonal elements, while the B elements being the same along the diagonal. Let's talk about its three breakdowns. Here is the Q matrix which we had seen. This is nothing but a matrix with the eigenvectors as column vectors and forming an orthonormal matrix. This will essentially rotate standard basis to align with the eigenvectors. Second matrix, that is the lambda matrix, is a diagonal matrix with eigenvalues along its diagonal elements. Scales the x-axis with lambda 1 and lambda 2 for the y-axis. The final Q transpose matrix is a transpose or inverse of eigenvector matrix Q. This rotates eigenvectors to align with the standard basis. Let's see how this actually occurs by taking an example. Talking about a matrix S4224, we can see that we can break it down in Q lambda Q transpose as such, where root 2 upon 2 and root 2 upon 2 is the first eigenvector for the matrix S, minus root 2 upon 2 and root 2 upon 2 is the second eigenvector for the matrix X. And corresponding eigenvalues are 6 and 2. Similarly, this is nothing but the transpose of the eigenvectors taken in Q as column vectors. Let's see how these transformations actually happen. This visualization is a core aspect of our understanding of the concepts that applied linear algebra offers to us. So we can see that the matrix S actually represents a net transformation. A simple 2D plane revolves through many transformations, which will lead to it forming this particular figure as we see. Now, exploring its decomposition and seeing the transformations in its elementary form is what we are going to do. Taking upon the first transformation, this will rotate the plane from its eigenbasis to its standard basis. This is where the 90-degree angle comes into play. Now, the lambda matrix will scale each axis with its respected scaling factor. Finally, the Q matrix would be rotating the standard basis back to the eigenvector's original basis. This is how ultimately we are able to achieve the net transformation by applying these subtle transformations in that particular order. And this is so deep and interesting to study as this actually lies outside the boundaries of mathematics, where we are talking about conceptual understanding at its peak. So, the final representation that spectral decomposition talks about is that every symmetric matrix A can be written as A equal to the Q matrix, which is nothing but the eigenvector matrix, the lambda matrix, that is the lambda values along the diagonal elements, and the Q transpose matrix, that is the transpose of the eigenvector matrix. But when we simplify this, we are able to achieve an equation, an expression which has a deep significance of its own. We can see that we can write it as lambda 1 x1 x1 transpose plus lambda 2 x2 x2 transpose so on till lambda n xn xn transpose, where x1 x2 xn are the n orthonormal eigenvectors of A. They are the principal axis of A. What this means is that xi transpose is the projection matrix onto xi. Now, this is so mind blowing as we are now able to achieve the matrix in the form of its projections along its eigenvector basis. We are able to scale the eigenvectors to achieve the original matrix that we are talking about. This is what spectral decomposition actually is. This is what it actually means. Let's talk about this process of eigenprojection further. Let X be an n cross n matrix. This is something I've written to prove this theory on my own. Let X be an n cross n matrix which is symmetric with eigenvalues lambda 1, lambda 2, so on till lambda n, and eigenvectors v1, v2, so on till vn. Then X equal to PDP transpose. This is nothing but the spectral decomposition expression that we encountered previously, where P would be the eigenvector matrix and D would be the diagonal matrix with eigenvalues as its diagonal elements. But the thing is, not all eigenvalues are always unique. Some of them might be duplicate of one another. So let us consider that k of them are unique and let us take them as the form of del 1, del 2, and so on till del k with multiplicity r1, r2, so on till rk. PDP transpose can thus be written as the original form and which would lead us to the expression which we encountered in the previous slide. But not all of these are unique terms. What do we do now? That's where this process of recombining the terms occurs. What we'll do is let us assume that lambda 1 and lambda 2 were nothing but duplicate values of the same del 1 value. So we can combine the eigenvectors of them to form this projection matrix corresponding to del 1. Similarly, we can get the corresponding projection matrix of corresponding to del 2 if we consider lambda 1, lambda 2, lambda 3 being duplicate values of the very same eigenvalue, and so on for the k values of del. We can see that we are finally able to achieve the again projection matrix onto the column space of the matrix associated to lambda I. That is, we are able to project our matrix again in terms of unique eigenvector spans. And that is amazing in its very own form. Let's talk about the algorithm for spectral decomposition. Algorithms are really important as these form the basis for the pseudocode that we write as for linear algebra's applications in real life problems. This can be in any programming languages. We'll be discussing it with Python. So first of all, the step one will be involving eigenvalues by solving modulus a minus lambda I equal to 0. This is nothing but the characteristic equation we are so familiar with. Step 2 involves finding the corresponding eigenvectors by solving A v equal to lambda v. This can be simplified as A minus lambda I into v equal to 0, which can then be solved by using the Gaussian elimination method that we have studied so long ago. Step 3 form the diagonal matrix with lambda I and the matrix P with eigenvectors as columns. Step 4 orthogonalize P and take its transform to form P transpose. Step 5 is express the transformation as scaled projections onto eigenvector basis. This is the end of the spectral decomposition algorithm. Let's see how we actually code it now. Let's now move on to the Python code for spectral decomposition. Now, we all must be somewhat familiar with the open source library of NumPy, and it offers a really efficient method to deal with this problem. We talk about the np.lenal.ig method, which serves as the function to return the lambda values, that is the eigenvalues, and the corresponding set of eigenvectors. When I took upon a random matrix M, I applied this function on it to achieve the corresponding eigenvectors in the column vectors form and the lambda values according to it. Now, how can you verify it? It's by reconstructing the original matrix from the spectral decomposition form. That will verify our entire theory. Let's have a look at that. Generating P transpose would be by simply taking the inverse of the eigenvector matrix that we achieved previously. That is what is the case for orthogonal matrices. Generating lambda would be diagonalizing the eigenvalues to form a 3 cross 3 matrix corresponding to the dimensions of the original matrix. Now, reconstructing the original matrix involves taking dot products of the U matrix with lambda and U transpose matrix. That is, we can achieve a matrix of this particular form. But we see that the original matrix is nothing but exactly the same. Thus, we can verify our spectral decomposition process and appreciate its validity. Now, talking about brute forcing Python code for spectral decomposition. Because when you talk about applying NumPy, you can't actually process the time complexity, right? You need to understand what process is actually going on in the backend to actually understand how useful is coding this, how efficient is this. Now we understand that we talked about the process in the algorithm in step 2. While calculating eigenvectors, we will make use of the Gaussian elimination method that actually forms the very core process of this entire process because it is one of the most costly operations. Have a look at this. As we can see, we will be inputting the A matrix and the B matrix. That is, whenever we represent a vector equation in the form of Ax equal to B, this is what we will input, the matrix A and the vector B. We then create an augmented matrix AP and we will perform row echelon elimination to get an idea of the final values of to identify the free vectors to actually get the eigenvectors associated with our matrix. Now you can see in this process, in the step of partial pivoting, we can see that we have one for loop and another for loop nested within it. What this will contribute is actually a big O of n square. Going further, we see that when we tackle row scaling problem, we again come into a single nested loop within the IE loop. So this will again be contributing a big O of n square. So far, so good. Now, when talking about the final elimination process, we can see that we are encountering two subnested loops within the original for loop. What this will be doing is actually it will be contributing a big O of n cube. Thus, our net time complexity for the Gauss-Jordan elimination to find the eigenvectors becomes a big O of n cube. This is the entire code, and I'll actually be sharing a Jupyter notebook file in the description where tinkered with various forms and various processes of how to step by step come up with the process, the idea to do it by brute force. So you can definitely check that out as well. Now, talking about the time complexity once and for all. The standard way to analyze the algorithm involves the use of Gauss-Jordan elimination, which is big O of n cube. same as that of matrix multiplication. But with the growth of research interest, we have been able to optimize the complexity of matrix in multiplication. Now you can understand that research has actually enabled us to make this process more and more efficient. That is, a process so important to applied linear algebra has been made much more efficient than what it could have been. Let's talk about the Strasson's algorithm. This has helped us achieve a big O of n to the power 2.807. Similarly, Coppersmith-Winograd algorithm helped us achieve a much better time complexity of big O of n to the power 2.376. Further optimizations along the Coppersmith-Winograd algorithm led us even to improve a bit and bring it down to big O of n to the power 2.373. Now, talking about Coppersmith-Winograd algorithm, it actually involves complex mathematics, which is particularly beyond the scope of this course. But I'd still like to discuss a slight idea of what Strasson's algorithms do. It actually divides the matrix into four different halves. Now we are talking about an n by 2 order matrix in four different parts. What this does is we can represent the original transformation which took eight equations, now compressing them down to only seven equations. Hence, we can consider the time complexity as big O of n to the power log base to 7. That is, now we are simply solving seven equations, and thus we are still getting the same result. That leads us to big O of n to the power 2.807. I hope you found it interesting just as much as I did. Now, every good thing often comes with a shortcoming. So does spectral decomposition. That's why it actually is the very starting point to the entire world that linear algebra offers to us. Applicable only to symmetric matrices, we cannot always expect to deal with a symmetric matrix in linear algebra. This is a major shortcoming where spectral decomposition comes to. That is, we cannot expand its applications to any kind of matrix. We need a symmetric matrix and we need it to be squared, which is automatically implied. But how to deal with it? This shortcoming is actually catered to by a singular value decomposition. That is the SVD process. So we finally achieved the bridge where we will now be going on to many applications of spectral decomposition. How it has opened enormous opportunities to the world of mathematics and machine learning for us. Let's see some of its applications and how it has improved many processes for us. Applications will firstly involve the very essence of spectral decomposition, which marks the beginning of a long lineage of improvements and research, which has led to innovative strategies like the SVD and PCA. SVD standing for singular value decomposition and PCA standing for principal component analysis, which are the evergreen algorithms of machine learning and deep learning as well. And these are surprisingly accurate even when other models fail. This process also helps us to get power of matrices faster. Now, this we have been familiar since semester one as well, where we would use the simple process of eigen decomposition, which was particular to any matrix, and we could simply take the power for the net transformation upon the diagonal matrix only, because such powers can easily be shifted along only the diagonal elements. That is, a to the power k would only be lambda to the power k for each diagonal element lambda I. Finally, a really interesting aspect that spectral decomposition offers is that it helps to solve linear equations faster. Now, whenever we talk about any computational processes, we need it to be efficient. We need it to be fast. That's where spectral decomposition can step in. Talking about the process, let's consider the example of OLS estimation. Our goal is to solve the following for B. First of all, let's talk about what OLS estimation actually stands for. OLS is nothing but ordinary least squares. Yes, we are talking about the process of linear regression, which we all as ML engineers have stepped into at some point of time. Consider the expression x transpose x b equal to x transpose y, where b is actually the expressions we are trying to get. Since x transpose x is a square matrix and it is symmetric as well. We can decompose it into PDP transpose. This is the spectral decomposition form of this matrix. Thus, PDP transpose B would be equal to X transpose Y. Taking it further, we are aiming to find the values of B. Thus, we'll have to multiply by the inverse of PDP transpose. That is, we are trying to neutralize the LHS so that we can find the very exact value of B. The V value would then cause a term of PDP transpose whole inverse on the RHS as well. When we explore this, we know that opening the brackets would lead to an inversion of the expression. That is, we end up with V equal to P transpose whole inverse, D inverse, P inverse X transpose Y, which can further be simplified to P D inverse P transpose X transpose Y. That is, because P transpose is nothing but P inverse for our particular matrix, and P inverse is equal to P transpose. So yes, we can achieve this final operation. The orthogonal P matrix makes this computationally easier to solve. Moreover, since D is a diagonal matrix, the inverse is also computationally very cheap to calculate, because the inverse would simply be equivalent to converting each lambda I as the diagonal element to its simple inverse, thus achieving a much faster computational result. With this, let's put an end to this topic. I'd like to talk upon the references which have helped me to share my experience of this topic with you all. First of all, I'd like to thank my professor, Dr. Mayank Goswami, who actually has given us a really different aspect to look at what linear algebra offers to us. We would never have thought to go so in depth of the concept to express a matrix as a transformation, to express a spectral decomposition as a projection matrix on a vector space, and so much more. This world has been opened us to us by our very mentor. Secondly, I'd like to put my credits onto the Visual Kernel channel of YouTube, which has helped me to place some visualizations for you guys as well and help us thorough our concepts from the base down. Thirdly, I'd like to mention the open source software of MANAV, which is a Python-based software where we actually can program to create visualizations corresponding to the different concepts of linear algebra. And it is very, very effective to understand any topic in deep depth and provide accurate and apt visualizations for it. So thank you for sticking around, and let's just keep exploring linear algebra with much more to come.